So on number 1, we are supposed to solve this system. We've got 3 ways of solving a system of equations: graphing, linear combination, or substitution. Which one do you guys want to use on this system today?
Substitution.
Yes. Substitution. I agree that that's probably our best bet for today, because we have one of the equations that has a variable that has been isolated. The y is all alone on one side. So we have something that's telling us the value of y. That means we can make even exchanges. Y is equal to, has a value of 3x minus 2. So I can come down here and make it take the place of this y right here. These y's are the same. All right, so I would have x plus 2, and then I would make my substitution. Instead of writing the letter y, I'm going to substitute something that has equal value, 3x minus 2, and then I recopy my equals 3. What can I do with it now that I couldn't do before? Now I can distribute. I'm going to distribute the 2 to each piece. So I would have x plus 6x minus 4 equals 3. What next? Yes, ma'am. Combine our like terms. What do we get when we combine our 2 like terms together? 7x. We're adding them. Remember, when the exponent changes, that means I've multiplied things together. When the coefficient, the number out front, changes, that means I've added things together. So 7x minus 4 equals 3. Yes, ma'am. Add 4 on both sides. So I get 7x equals 7, which means x is what? X is 1. Divide both sides by 7, and x equals 1. Are we done?
Oh, no, you have to substitute.
We have to substitute back in because we want to find what next? Y. Does it matter which equation we use to find y?
No.
Which one do you guys want to use? Top one sounds good. That top equation was y equals 3x minus 2. In the place of the x, we're going to put what? 1. 3 times 1 is 3. So I have y equals 3 minus 2. Y also equals 1. What would this look like if we had chosen to solve it by graphing? What would we see? Where would you look for solutions if we graphed it?
You'd watch where the 2 lines intersect.
Where the 2 lines intersect. How many places do these 2 lines intersect?
1 spot.
1 spot. But we found an answer for x and an answer for y. Doesn't that mean 2 solutions? No. Because they only cross in how many points? 1 point. That ordered pair, that point, we have to have coordinates for both the x and the y part, but it's still describing just one place where they cross each other. So this is 1 solution. And it would be what ordered pair? 1, 1. Awesome. Number 2, simplify completely. Where would I want to start on this? Yep, keep, change, flip is where I would start. Keep, this is division, so change. And this guy right here, we're going to flip. I'm going to bring that over to the left as well. So 2x squared minus 50 over 4x squared minus 16x minus 20. There's my keep. And then change means I'm going to have multiplication and then flip. The 6 comes up to my numerator. 3x plus 15 moves down into my denominator. All right, so I did keep, change, flip. What do I want to do next? Factor. And when we go to factor, we always look for what first? GCFs. Do any of these have GCFs?
Yes.
Yes. Does the first numerator have a GCF? What is the GCF of the first numerator? 2. So I'd have 2, and then what I have left over is x squared minus 25. Does the first denominator have a GCF? 4. So I'm going to bring that out to the front. That would leave me with x squared minus 4x minus 5. Bring down my multiplication. Second numerator is just what? It's just by itself. It's just a 6. So we're just going to leave it alone. Does the second denominator have a GCF? Yes. What can go into both pieces? GCF of 3. So we're going to bring that out to the front. And that would leave me x plus 5. So far, so good? All right. Is there anything else that still needs to be factored? First denominator. And what else? First numerator. How do you know by looking at them that they still need to be factored? Yep. We have our x squareds here. This numerator, does anybody remember what we call that?
Square root.
Not square root, but close.
Quadratic.
It is quadratic. Difference of perfect squares. And so we are going to use a square root here. Yes. Difference of perfect squares. I had my GCF of 2 out at the front. How will this factor? X plus 5, x minus 5. Because 5 times 5 would give me 25. If I do positive 5 times negative 5, that's what that plus and minus do. I get the negative 25 that I see there. All right, over. I'm going to keep that 4 out at the front here. Let's go to factor this guy. I'm going to need my x. Can I use a shortcut here on that first numerator? Or sorry, denominator? Since I got the 4 out, can I use the shortcut? Yes. If I hadn't taken the GCF out, then no. But taking that GCF out means that I can use my shortcut. I need 2 numbers that multiply to give me negative 5. But when I add them, I get negative 4. What will multiply to negative 5 but add to negative 4? What multiplies to 5? 5 and 1. Negative 5, positive 1. My b value is negative, so the bigger number has to be a negative. All right, so I would have x minus 5, x plus 1. Second fraction, we already factored everything there. I had 6 up on top, 3, and x plus 5. What do I do with it from here? I can cross out the x minus 5s and the x plus 5s. What do I have left in my numerator then? 12, because I have 2 times 6 left in my numerator, right? What do we have left on the bottom? Yep, I have 4 times 3. Anything else left? Times x plus 1. So you said that this is 12, but this is also 12. That will cancel. 12 divided by 12 is what? 1. So what would my final answer be then? On the top or on the bottom? 1 over x plus 1. The x plus 1 is down in my denominator. It does not flip sides just because there's nothing up on top. Whenever everybody up on top cancels out, we still have a 1 up there. All right. We are going to start our next unit today. I want you guys to flip forward in your books to page 246. We're going to look at a couple of these to get us started, and then we'll dig in a little further. Page 246. You go to the snack bar and you buy a bagel and a drink for lunch. You can choose from a plain bagel, a blueberry bagel, or a raisin bagel. The choices for drink include water or a sports drink. How many different snacks could be made with these choices? How many different snacks could be made with these choices? Yes. 6 different snacks. Let's talk about why. You walk up to the snack bar, and let's imagine for just a moment that you chose the plain bagel. After you choose the plain bagel, you still need to make what choice? Your drink. And what are your options for your drink? Water or a sports drink. You guys like my little drinks there? So we have altogether 2 options here, right? 2 choices. What about if you chose the blueberry bagel? Yeah. Blueberry bagel, but then you still have to choose between the water and the sports drink. And so that would also be 2 lunches. Or the raisin bagel. You go with the raisin bagel and then you still choose water or sports drink. And so we end up with an additional 2 lunches here. So altogether we have 6 total options for lunch. Now you might look at this and say things like, it's a bagel and a drink. That's 1 lunch. But we want to look at all the little differences that might matter to somebody. So technically we have 6 different available lunches. Can you guys think of how we could have gotten to this 6 options a slightly faster way rather than drawing it out?
By multiplying the amount of bagels by the amount of drinks.
Yes. We can multiply the options for bagels, which is 3, times all of the choices for drinks, which was 2, and we get the 6 lunches here. This is called the fundamental counting principle. It's how I figure out the grand total of all the possible things that could happen. I look at how many options I have for each choice that needs to be made, and I multiply all of those choices together. Let's look at number 2. When you get ready to get dressed for school, you open your closet and find out that you have the following choices: a red shirt, a blue shirt or a white shirt, jeans or sweatpants, tennis shoes or sandals. How many different outfits could be made with these choices? 12. Tell me how you got there.
So I multiplied the red, blue, and white, which was 3, times the jeans and sweatpants, which was 2, and tennis shoes and sandals, which was 2.
Yes. We're looking at how many choices we have available to us at each stop. You have 3 options for your shirt, 2 options for your pants, 2 options for your shoes. When you multiply all those together, you get 12 total outfits. If I knew that, you'd talked to me about this before, I knew that this was your option every day. If I knew that you had 12 total outfits, what's the probability, what's the likelihood that I guess on the first try which outfit you decided on? 1 out of 12. This 1 up on top would be the 1 outfit I guess. Out of 12 total possible outfits. We are going to be talking about probability in this unit. In fact, I want to go and define that and practice a little bit with it, and then we're going to come back to this page. But for just the next couple minutes, I want you guys to flip to page 238. Question number 1 actually has something different written there, but we're going to define probability there. On page 238, we're going to define a probability there. What is a probability? How do you guys think about probabilities? Yes, sir.
Percentage.
Percentage. Anybody else? Yes.
Like guesses.
Like guesses. Anybody else want to offer up? I like everything I've heard so far. This is the way we're going to formally define it. The chance that a given event will occur, which we can write as a percent, we can write as a decimal, or we can write as a ratio or a proportion. So this is the chance that a given event will occur. We express this or write it as a ratio decimal or percent. How do you calculate a probability? You guys just told me a moment ago the probability that on the first guess I would get your outfit right. And you said that was what?
It's the amount of events that can occur within the amount of possible, like over the amount of possible.
Yes. Yes, yes, yes. Okay, so here's how we're going to talk about this. You're absolutely correct. We use something called probability notation so that everybody else knows that we mean we're talking about the chances of something. When we're talking about a probability, we use a big capital P, and then inside parentheses we say what it is that we want to happen. So we'd have the event in here. We usually set this up as a ratio or as a proportion. And up on top of our proportion, we have all the ways that the event can occur. In the numerator, the number of ways that what I'm interested in happening can indeed happen. Down on the bottom, we have the total number of possible things. So if I'm thinking about this, I'm going to go back to that bagel example for just a moment as we think about this. You go, you pick out your lunch, you pick out your bagel and your drink, but your friend handed you some money and said, hey, can you bring me back a bagel and a drink as well? And you're like, what kind would you like? And they're like, I don't care. But while you're gone, they change their mind. And they're like, only way I'm going to be happy is if they bring me back a raisin bagel. I don't care whether I get the sports drink or the water. Definitely want a raisin bagel. How many different ways could that be made true? Them getting a raisin bagel. So let's think about all 6 of those options that we had. 2 out of 6, because you either come back with a raisin bagel and a water, or a raisin bagel and a sports drink, and either one of those make them happy. You come back with any of the other bagels, and they're going to be like, oh, okay. So we would have probability of raisin bagel is equal to, there's 2 ways that this could happen out of 6 total possibilities. So this is how we write a probability statement, and then what our proportions or our ratios look like. When we write them as proportions like this is going to be the only time you guys ever hear me say this is during this unit. Please do not reduce your fractions. Because when I'm talking about probabilities, the numerator has a real meaning in my context. I don't want to reduce it down necessarily. This means there are 2 different things that could be brought back that make me happy. The denominator has a very specific meaning here. It tells me that there's 6 total choices. And while you could reduce it, it has the same mathematical value, it doesn't give me as much information when I reduce that down. What would this be if we decided to write it as a percent? About 1/3, so like 33%, right? I want to look at this. This is number 3 on your page. So I have a marble jar. I've got these marbles in it. And if you reach into the jar blindfolded and you choose the correct color, you win. How many total outcomes are there? Ooh, I've got 2 different answers, and I like them both. I heard 12, and I heard 3.
Wait, what was the question?
How many total outcomes are there?
Are there 36?
It's not 36. It is 12, but we'll talk about the 3 here in just a moment. There are 12 total possible outcomes. 12 outcomes of you reaching into the jar. Yes, sorry, my apologies. The color would be like, if you imagine a silly little game show or game, you've got a blindfold on. After the blindfold goes on, the color flashes behind you. So everybody in the audience knows what color you should be reaching for, but you don't have any idea. You reach into that jar, and all you know is that you feel 12 different round objects. So 12 possible outcomes, because you're going to grab how many of those marbles? You're going to grab one of those out of the 12. There are 3 distinct or different outcomes. But when I'm talking about the total number, there are 12. Does that make sense? Yeah, because once that blindfold goes on, you don't know which is which. And if they didn't show you the jar beforehand, they just said, reach into the jar. If you grab the right color, you win. You're like, how many colors are there? They're like, blindfold goes on. You don't know. For all you know, there's 12 different colors because all you can do is reach into that jar and feel the different shapes. Does that make sense? I want to write the probability of choosing each of these different colors here. So knowing that there are 12 total possible outcomes, what would be the probability that we reach in and we choose a green one?
6 out of 12.
6 out of 12. Why 6 out of 12?
There's 6 green marbles.
There's 6 green marbles out of 12 total. So this is all the ways I can choose green. Out of the total marbles. What about yellow? Just 2? Like this? 2 out of 12. What about blue? 4 over 12, 4 out of 12. We're always going to be talking about our probabilities as something out of something or something over something. Which color would give you the best chance of winning? Green. We said our probability of winning with green was 6 out of 12. How would we express that as a decimal?
20%.
Yeah. 0.5, or as a percent, 50%, or you could say 1/2 even. So we can express it as a proportion, as a ratio. We can express it as a decimal. We can express it as a percent. What's the chance that you reach into this marble jar that I've described right here and you grab a purple marble? 0 out of 12. This is called an impossible event. This is the top of the next page. Something that cannot happen. If I wrote 0 out of 12, what would that, I know I said don't reduce, but if I asked you to write it as a decimal or as a percent, what would it be?
0.
Just 0. What's the chance that you reach into the jar and you grab a marble?
That's all out of 12.
12 out of 12 chance. This is called a certain event or a guaranteed event. So you reach into the jar, you definitely grab a marble. You've got a 12 out of 12 chance of getting one of those 3 colors. What would that be if I asked you to write it as a decimal? 1 or 100%. When we're talking about percents, it's going to go anywhere between 0% and 100%. When we're talking decimals, it's going to be between 0 and 1, because our fraction would be something like 12 out of 12. Does that make sense? All right. I want to practice just one more with writing some probabilities, and then we're going to go back to that first page and practice a little bit more. So right down here on the bottom, Isa, I've got this spinner in a game. What's the chance that when I spin this spinner, I land on a 5? 2 out of 5 chance. Question. Is this a 5 right here because this is a 5 right here?
No.
So why is this a 5?
Because it has 5 little ones.
Yes, there are 5 options on the spinner. Even though some of them have the same number in them, there are 5 different little pie-shaped wedges. All right, second one over here. I've got a die, just a normal, regular die, no tricks. How many sides are on a regular die? 6 sides. What's the chances that when I grab that die and I roll it one time, I get an 8? 0. Why 0? There's not an 8 on there. It's got a 1, a 2, a 3, a 4, a 5, and a 6. There are no 8s on that die because it only has 6 sides. Marble jar. What's the chance I reach in here and when I come out with one of those marbles, it has the letter A on it? 5 out of 7. What's the chance that when I flip the penny, it lands on tails? 1 out of 2. All right. I want you to flip back to that page that we were on to start with, 246. The math club is selecting new officers. 3 people are running for president. 4 people are running for vice president. 4 people are running for secretary. And 2 people are running for treasurer. I want to know all the different arrangements that would be possible with these people on the ballot. How much? 96. Tell me how you got there.
I multiplied 3. Well, first I did 4 times 4, which is 16. Then I multiplied 3. And I got 48. Then I multiplied 48 times 2. And got 96.
Yes. We take all the possibilities, multiply them together. So every choice along the way on that ballot. 96 total different arrangements. Okay, so if you look at the next one down, number 4, they've held the election. Somebody won the job of president. Somebody won vice president. Somebody won for secretary, and somebody won for treasurer. So how many people now are actually holding those offices? 4. They are going to go and have their picture taken for the yearbook. So we've got 4 total people that need to go have their picture taken, and they're going to do it as a group. The photographer says, all right, I need you guys to line up. He doesn't care how they line up, just as long as they get in line, and then when they're done, they write their names down so that he can get them in the right order in the yearbook. Somebody has to make a decision, right? Somebody will be the first to say, well, I'm standing right here. How many possible people could be first in line?
4 out of 96.
Well, 96 was the total number of ways that this election could turn out. But there are 4 people that could be first in line. Yes, sir.
It could be 16 total, like, ways they can stand in line.
Close. Very close.
Because it's not 16.
It's not 16. Once a single person in that group makes a decision, I'm standing here. How many people are now left to be second in line? 3 people. So far. Once the first person has made their choice and the second person has made their choice, how many people are there left that could be third in line? 2. And then by default, that last person, how many people are last? Just 1. So I do 4 times 3 times 2 times 1 because somebody has to make that first choice. But once they make a decision about, I'm standing here, there's now 1 less person that needs to make a choice. Yes, sir. 24. This idea right here, where every time you make a choice, and that means the number of options that are available the next time is 1 less, this is called a factorial. Factorial starts with the largest number of possibilities, and then it goes down by 1, down by 1, down by 1, down by 1, until you get down to the very last choice where there's only 1 option. We can express this idea of factorial by writing the largest number of choices at the beginning, and then we put an exclamation point at the end. This is called a factorial. Here's my factorial notation. Why do they stop at 1 and not go all the way to 0? Yeah, we can't have the 0th person in line. What would happen if we multiplied by 0? It would give us 0. It's saying that there's no way that this could happen. Well, there's definitely a way that this can happen. All right, guys, we will pick up here tomorrow. We'll keep talking about factorial and fundamental counting principle. Monday is when your first homework assignment of this unit is due. We've talked about quite a few pieces that are there. Tomorrow, we're going to touch on Venn diagrams. Does anybody know what a Venn diagram is? Have you guys ever seen those pictures with the overlapping circles? That's a Venn diagram. So we'll talk about probabilities and Venn diagrams tomorrow.